Hello and welcome back. Today we'll be discussing Chapter 5 of Klein Organic Chemistry, and this chapter introduces stereoisomerism. So there are generally two different types of isomers that we're going to be dealing with in organic chemistry. There are constitutional isomers and there are stereoisomers. Constitutional isomers have the same molecular formula but a different connectivity of the atoms. So these are completely different molecules. Stereoisomers have the same molecular formula and they have the same connectivity, but they have different arrangements in space. Okay, so these may be very similar molecules, and we're going to look at the different types of stereoisomers in this chapter. So although two molecules have the same connectivity, they may not be identical. So these in fact are stereoisomers here. Here we have two examples of 1,2-dimethylcyclohexane, but notice the molecule on the left has methyl groups, right? Both on a six-membered ring, okay? And these methyl groups are on the same side of that six-membered ring, okay? And they're fixed there. You can't just do a ring flip and one goes to the other side. Here on the right, we have the methyl groups on opposite sides of the six-membered ring here. So this is trans 1,2-dimethylcyclohexane. So if they're on the same side, it's called cis, and if they're on opposite sides of the ring, it's called trans. So in order to give these two compounds unique names, because they're different compounds, we use the terms cis and trans. And that stereochemistry goes out in front of the name of the molecule. So carbon-carbon double bonds don't freely rotate like carbon-carbon single bonds do. So although these two molecules have the same connectivity, they are also stereoisomers. They're not identical because we don't have free rotation at the double bonds in these molecules. And so here we have two examples of 2-butene. We have 1, 2, 3, 4 carbons in the chain, the parent chain, and we have a double bond between carbons 2 and 3. So this is 2-butene on the left and 2-butene on the right. But these carbons are fixed in this position due to that lack of free rotation about a double bond. So the molecule on the left has the methyl groups on the same side, and so this is cis 2-butene. The molecule on the right has the methyl groups on opposite sides. So this is trans 2-butene. Notice also that the hydrogens are on the same side or opposite sides, respectively, and hydrogens are also qualifiers for cis and trans. So we'll talk about that a little bit more later on. So let's identify the following pairs of molecules as either constitutional isomers, stereoisomers, or identical structures. So this first molecule, A, has a six-membered ring, so these are both cyclohexane molecules, and they each have an OH group on them, and the OH group is pointing up. Of course, it doesn't matter if we flip it over, they would still be the same molecule, right? So these are actually the same. The only difference between the two is that they've undergone a ring flip, which happens at room temperature with cyclohexane rings. So for molecule B, we have this double bond. The left side of the double bond has two methyl groups. The right side has a methyl and a hydrogen. Notice on the other molecule, the left has two methyls and the right side has a methyl and a hydrogen. If we took this molecule on the right and flip it over, then slide it over onto the other, this would be obviously exactly the same molecule. This methyl group would go here, this methyl group would go here, this methyl group would be superimposed on that one. These are the same molecules, and it helps to make a model so that you can prove this to yourself. Okay, the next molecules we have, we'll call this pair C. These cyclohexane rings have two OH groups attached. But remember, okay, these hydrogens, let's draw the hydrogens in. Okay, Okay, so these OH groups on the left are actually on the same side of the ring, and these OH groups on the right are on opposite sides of the ring. Okay, so this one on the left is cis, and the one on the right is trans. So these are different. Okay, these are actually stereo isomers. They have the same connectivity, but different arrangements in space. So what about this molecule set we'll call D? We have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons in both of them. And we have a double bond between the second and third carbons in both of them. But the first molecule has hydrogens on opposite sides. The second molecule has hydrogens on the same side. So the first one is trans 2-pentene. The second one is cis 2-pentene. The next set of molecules doesn't even have the same connectivity. The first one is a 5-membered ring. The second one does not even have a ring. So these are completely different. These are actually constitutional isomers. Okay, so the answers are here on this slide. So let's consider the double bonds and rings and classify them as cis, trans, or neither, which we already did actually. This first one, A, we have hydrogens on the same side, so that's cis. Okay, that's not drawn very well. This molecule B, we have the OHs on opposite sides of the ring, so it's trans. The next molecule we'll call C. The OHs are on the same side, so they're cis. The next one, D, is interesting. Since you can rotate it around and put it back on top of itself, this is actually neither. Another key here is that we have 2 methyl groups on the same carbon. So if you have 2 of the same groups on the same carbon of a double bond, then it's neither. It's neither cis nor trans because you'll be able to rotate it around on top of itself. And it's helpful here to make a model. Okay, so the next molecule, call that E, has hydrogens on opposite sides, so it's trans. Alright, so there are other different types of stereochemistry. We've seen cis and trans stereochemistry, but another type is called an asymmetric center or a chiral carbon. Okay, so a chiral object means that it's not the same as its mirror image. A chiral object has a non-superimposable mirror image, so you can test to see whether objects are chiral or identical to see if their mirror image is superimposable. And it's really going to help if you get a model kit to do this. Okay, so we're going to look at that in just a minute what it means, but let's just preliminary, we're going to have some definitions. Chirality is important because 2 chiral molecules can be mirror images of each other, and they'll have different properties, okay, because they're not identical. Their pharmacology may be very different. For example, 2 mirror image molecules that are not superimposable are called enantiomers. We'll talk about that again in just a minute, but enantiomers may not necessarily activate the same receptor in a biological system. So it's very important that we have the correct enantiomer of a molecule. It's really helpful if you'll get some handheld models to do these exercises. So chirality usually results when a carbon atom is bonded to 4 unique groups of atoms. So in other words, a chiral carbon has 4 different things attached. Okay, so here we have this molecule, which you can see on the right. This carbon has an OH group, a hydrogen, a methyl, and an ethyl. Okay, we have that represented on the left with this handheld model with a red ball. Okay, in this case we have a blue ball, a white ball, and a green ball. So you can use a carbon with 4 different things attached to represent a chiral center. Okay, with 4 different balls attached to represent any chiral center, and it will help you in visualizing these molecules. So notice that the molecule on the right also has the red, blue, green, and white balls, and that these are actually mirror images of each other. But if I flipped one of them around on top of the other, they're not going to exactly fit back on top of each other. So these are actually non-superimposable mirror images. Therefore, they have a special name. They're called enantiomers. Non-superimposable mirror images are called enantiomers. So in an atom like carbon that has a tetrahedral center, it has to be an sp3 hybridized carbon because it has to have 4 different groups attached. When it has a chirality center, then it's going to have the ability to have an enantiomer. So let's see if any of these molecules have a chirality center. So first the molecule on the left, okay, this molecule is a derivative of butane. This is 2-chlorobutane, okay, and it has a chlorine attached at the second carbon. So what is attached at this carbon? We've got chlorine, hydrogen, methyl, ethyl. So there are in fact 4 different groups attached to that carbon, so this carbon is chiral. The next molecule has an OH group, a hydrogen, an ethyl, and a propyl group. So there are 4 different things attached, so this is a chiral carbon. The next molecule, that carbon that's highlighted, has a bromine, a hydrogen, this path around the molecule, and notice that the path on the left is different from the path on the right, because as I move left around the molecule, this carbon is sp3 hybridized. As I move right, I have a double bond. Okay, so I'm not considering those to be part of my chiral center, but because they are attached to that chiral center, they are different, and they're different. I have a chiral center here. Okay, now an sp2 hybridized carbon itself can't be a chiral center, but this one is not on the chiral center, it's attached to it, and so that's going to be one of my 4 different groups. Let's see if we can identify the chiral centers in the molecules below, so they can be called chiral centers or chirality centers. Alright, so let's look at molecule A. We have that cyclohexanol again. This carbon, so first of all, let's look at the rest of the molecule. All of the other carbons have 2 hydrogens, and remember we have to have 4 different groups attached for a molecule to be chiral. If there are 2 of the same groups, it may have a mirror image, but they'll be superimposable. So you should make a model to prove that to yourself. If 2 of the groups are the same, you can superimpose them. Okay? But this carbon here is the one in question because it may have 4 different groups attached. So let's look at it a little bit further. So here we have OH, hydrogen, and this half of the molecule, and then we have this half of the molecule. Well, notice that as we go around the lower side, we have carbon, carbon, carbon. Okay, CH2, CH2, CH2. And as we go around the upper side, we've got CH2, CH2, CH2. So these 2 paths are the same, and therefore this molecule, this carbon, is not a chiral center. That molecule is a chiral. And we're going to examine why that is further in just one of the next videos coming up. But because these paths are the same, that is not a chiral center, making that molecule achiral. So let's look at molecule B. So we have this OH group here. Okay, so let's call this carbon 1. Now this carbon has hydrogen, OH, this path around the molecule, okay, and the upper path. So these two paths are different. As I go this way, I've got carbon, 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 and as I go this way, okay, I've got a carbon with an OH group and then then a CH2, then a CH2. So as I go on the lower path, I've got CH2, CH2, CH2. As I go on the upper path, I've got CHOH, then CH2, then CH2. So these paths are different, therefore that is a chiral center. So there's one chiral center in that molecule. Alright, let's look at C here, okay? So we have basically 3 carbons in question. So obviously this carbon on the end has 3 hydrogens, so it's not going to be a chiral center. We need 4 different things attached. And these other 2 carbons also have more than 1 hydrogen, therefore they cannot be a chiral center because they don't have 4 different things attached. So these 3 carbons in question, let's take a look at them independently. What's attached to that first carbon? Let's just do a different color on this guy, each one of them. Let's do dark green on that one. Okay, what's attached here? Going back, I have a hydrogen. Coming out, I have a methyl group. Over here, I have a methyl group, so that's a CH3. And then I have the rest of the molecule. Okay, so these methyl groups are the same. These methyl groups are the same, and therefore this carbon does not have 4 different things attached. So that's not a chiral center, even though they've drawn it with a wedge. So let's look at our next carbon. We'll do this one in red. Coming out, we have a hydrogen. Going back, we have a methyl. Okay, going to the right, we've got a carbon that has a hydrogen and a methyl. So this carbon has CH3 hydrogen, and then it also has another carbon. On the left, we have a carbon that has CH3, CH3 hydrogen. Okay, so this carbon on the right has the ethyl, methyl, hydrogen. Carbon on the left has methyl, methyl, hydrogen. So these paths right and left are different. So this carbon has 4 different things attached. So this is a chiral center. Okay, let's look at the next one here. Alright, so that carbon, I'll do in blue, has hydrogen, okay, methyl. Let me erase some of this junk that I've put up here. Let's erase some of this. Okay, so it's got hydrogen, methyl, ethyl, and then this part of the molecule, which is different. So there are 4 different things attached. So that is also a chiral center. So that molecule has 2 chiral centers. Alright, let's move to the molecule on the right. Let's start on the left side of the molecule. This carbon is sp3, but it has 3 hydrogens. This carbon has 3 hydrogens, so those cannot be chiral centers. This carbon has 3 hydrogens, and this carbon has 3 hydrogens, so those cannot be chiral centers. This carbon is sp2, and this carbon is sp2. sp2 cannot be a chiral center. So this carbon right here is a CH2, has 2 hydrogens on it. Okay, so that cannot be a chiral center. Alright, and so the the carbons that we have in question are this one and this one. Those are our potential chiral centers. So let's start with this one and see what's attached, okay? So we have methyl, this half of the molecule, and ethyl attached plus a hydrogen, okay? So that's 4 different things making this a chiral center, okay? Let's change colors and look at this carbon. This carbon has, coming out, it has a hydrogen. Going back, it has a methyl. Over here, it has an isopropyl. And over here, we have this thing with a double bond. Okay, so those are 4 different groups. So this is a chiral center. So that molecule also has 2 chiral centers. Let's identify and label all of the chiral centers in vitamin D. So again, we're only concerned with sp3 hybridized carbons, not sp, not sp2, because we need 4 different things attached. So that lets out this guy, this guy, this guy, this guy, this guy, this guy. Okay, so we're not concerned about those. We're also not concerned about any CH2s because they have 2 hydrogens, and so, or CH3s. So that lets out all of these. Okay. CH2s and CH3s do not count. Okay. So which ones do we possibly have to consider? This one. Let's move along. This one, this one, this one, and this one, and this one maybe. Okay. I forgot to mark this CH3 here as blue. Alright, so starting with the first carbon on the left, this carbon has hydrogen, OH, this path around the molecule, which is different from this path. So this is a chiral center. I'm going to block the chiral centers out in a square. Okay. Moving to the right, let's get a different color. This carbon has hydrogen, then it's got this path, which is different from this path, which is different from this path. So this is a chiral center. Next, this carbon has methyl, this path, and this path. And those 3 paths are different, so this is also a chiral center. Next we have, let's do an orange again, this carbon, which has hydrogen, okay, because remember it has to have 4 things attached because it's sp3. This path, which is different from this path, which is different from this path. So this is also a chiral center. Moving on, we have this carbon, okay, which has methyl, hydrogen, okay, this path, and this path. So it has 4 different things, so this is also a chiral center. And then going to the last one, we have hydrogen, this path, methyl, and methyl. So that is not a chiral center. So for vitamin D, vitamin D3, we have 1, 2, 3, 4, 5 chiral centers. Some of these biomolecules can be extremely complex, and the body makes the right enantiomer every time. Thank you for watching, and I'll see you in the next video.